to fully understand what I'm going to talk about, it's really vital that you do the interactive physiology programs on ventilation and gas transport. Now, I'm not going to require you to write anything and turn anything in on those, but nonetheless, you need to go through the information so what I talk about will make sense. Okay, so if you've done that, then let's talk about inspiration and expiration. Another term for inspiration would be inhaling. Another term for expiration would be exhaling. You know, even the terms inspiration, we often say something's inspired me or something's inspirational. And that actually comes from the thought that ideas or the breath of God gives us ideas. Whereas if we say somebody expired, or there's an expiration date on something, it means for expired, it kind of comes from the idea that somebody took their last breath. So these are kind of the origins of the words, but let's apply them to lung function, what's actually going on in the lungs. Now, first of all, we have to understand that there's something called Boyle's Law, a physics law that basically gives us the relationship between volume and pressure. And Boyle's Law summed up basically means if volume increases, pressure decreases, and if volume decreases, pressure increases. And that is really the key to how air comes into or out of a lung. So, what we're doing is we're comparing the pressure of the air inside of our lungs to the pressure of the atmospheric air, or the air and that pressure of the molecules of air outside of our bodies. So what we have to do, we know that molecules go from high pressure to low pressure. So what we've got to do is increase the pressure when we want to push it one way, or decrease the pressure when we want to push the air molecules a different way. So in inspiration, or air coming into our lungs, what we've got to do is we've got to make the volume bigger so the pressure is smaller. Well, how do we make the volume bigger? Well, what we do is we actually contract muscles, and the muscles we contract are the intercostal muscles, muscles between our ribs, and especially we contract our diaphragm. So if we want the volume to be bigger, we got to make the thoracic area larger, and we make them larger by the intercostal muscles kind of causing the whole thorax to lift up a little bit, and the diaphragm drops, creating more volume in the thoracic cavity. Now, if I create more volume, then my pressure is less. So what I've done is I've made the pressure less inside of my thoracic cavity so that the pressure of the air outside is higher, and therefore the air molecules will move from the higher pressure outside to the lower pressure inside of my lungs. Now, of course, if air is going to run into my lungs, I also have to have an ability to push air out of my lungs. So I primarily want the oxygen coming into my lungs, and I primarily want the carbon dioxide going out. Of course, there's also other gases within air, nitrogen actually being the main gas that is in air. We have more nitrogen in air than oxygen or carbon dioxide, but oxygen and carbon dioxide are the things that we primarily are using for the body. So we're concerned with getting more oxygen in, more carbon dioxide out. Okay, now, volume, if we're going to get air out of our lungs, volume of the air has to get smaller so the pressure increases. Remember, I want to get the pressure in my lungs higher than the pressure in the atmosphere, so it will move from the high pressure to the low pressure. So how do I increase the pressure in my lungs? Well, I make my thoracic cavity, where my lungs are, smaller, and that increases the pressure. So again here, how do I make them smaller? I contract external intercostal muscles, and I relax external intercostal muscles, and I relax the diaphragm, which causes the diaphragm to raise. When the diaphragm raises, the volume is smaller, therefore the pressure is increased. Now, when I increase the pressure inside my lungs to where it's higher than the pressure in the atmosphere, then the air has to move outside. So there's nothing magical about breathing as far as, your lungs don't inflate and deflate on their own, but instead your lungs inflate and deflate because there's a membrane called the pleural membrane with a visceral side against the lungs and a parietal side against the body wall. So what I've got to do, and also against the diaphragm, so what I've got to do is change the size of the body walls. And I do that again by contracting muscles. And then when they get larger, the membranes pull my lungs larger. When they get smaller, the membranes pull my lungs smaller. When I change the volume, it affects the pressure. Again, the bottom line is I need to change pressures because air always moves from high pressure to low pressure. So if I'm bringing air in, I need the air pressure to be higher on the outside, so it will go to the lower pressure inside. When I want to push air out, I need to make the pressure on the inside higher than the outside, so the air will go back out. And I do that by changing the volume. I change the volume by contracting muscles. Now, if you didn't quite understand that, you need to go back to that interactive physiology program because they actually show the process. And then if you're not sure then you can ask me questions. Now, the other program you need to watch, so I can sum it up here, is the program that talks about gas exchange. So the two gases we're really concerned about is carbon dioxide, CO2, and oxygen, O2. Now the first statement here, carbon dioxide is more soluble than oxygen, is real important because what that tells us is that carbon dioxide travels through water because we have a watery surface. Our blood is mostly water. The surfactant that lines our alveoli is mostly water. And so if I'm going to push carbon dioxide through the water, it actually pushes through the water easier than oxygen does. It is more soluble. What that means is that I need to exert less pressure on the gas molecules of carbon dioxide than I have to on oxygen. So I need less of a pressure difference of carbon dioxide on either side of the gradient for it to leave than oxygen. I have to have a higher pressure gradient for oxygen for it to be able to leave than I do for carbon dioxide. Carbon dioxide is more soluble, therefore it moves easier through water, therefore it doesn't require as much pressure gradient for that individual gas. Okay, now, in looking at oxygen, there's two major pathways in which oxygen comes from the alveoli into the blood. 1.5% of oxygen just goes directly into the plasma and stays in the plasma. Now that's a small percentage, but it is part of what oxygen is doing. But the majority of oxygen, 98.5% of oxygen, actually goes through from the alveoli into the plasma across the respiratory membrane. It joins hemoglobin. This HB here stands for hemoglobin. Oxygen joins it, and of course that's occurring in a red blood cell, and it forms a product called oxyhemoglobin. And basically the oxyhemoglobin carries the oxygen in the blood. Now we have 1.5% that's just floating around in the plasma, but most oxygen is being carried by the hemoglobin in the blood until our red blood cells get to an area where we're kind of oxygen depleted, and then this disconnects, and the equation actually runs the opposite direction, and so the oxygen would be removed from the hemoglobin, and then it would go into the cell and do whatever the cell needs to do with the oxygen, which is, as we know, it's to help with cellular respiration, help form more ATP. All right, but here again, there's basically two pathways. Very small percentage diffuses directly into the plasma. A high percentage joins hemoglobin in the red blood cell, forms oxyhemoglobin until it gets to the area. Because this is a loose bond, we want it to be loose because we don't want the hemoglobin to hold on to it forever. We want it to be able to give up the oxygen when the oxygen gets to a cellular area where it's needed. Okay, carbon dioxide actually has three pathways. Now, whereas only 1.5% of oxygen diffuse directly into plasma, 7% of carbon dioxide can diffuse directly in it. And part of the reason is because, as we said here, carbon dioxide is more soluble, therefore more of it can go directly into the plasma. Now, 23% of carbon dioxide kind of does what 98.5% of oxygen did. And as a matter of fact, after hemoglobin gives up oxygen and it's free, then the cells that are receiving the oxygen are usually giving up carbon dioxide. And so 23% of the carbon dioxide joins hemoglobin to form something called carbaminohemoglobin, HbCO2. It's called carbaminohemoglobin. And then, so 23% of carbon dioxide is joined to carbaminohemoglobin and just kind of circulates back up until it gets back to the lungs, where the hemoglobin releases it, gives off the carbon dioxide, and actually, at that point, picks up oxygen. All right, now, but the greatest amount of carbon dioxide actually goes into a red blood cell and joins with water. Now, there's an enzyme that facilitates that joining with water. It actually forms something called carbonic acid, H2CO3. Well, as we should know by now, acids are products that give off protons. Here's a proton. So this H2CO3, this carbonic acid, almost immediately after it's formed by these two joining, gives off a proton, and what's left over is what's called bicarbonate ion. So bicarbonate ion then actually leaves the red blood cell. It exchanges itself with a chloride ion. It leaves the red blood cell, and then it becomes a buffer for our blood. It becomes a base that helps buffer our blood and helps keep our blood at about a 7.4 pH on average for arterial blood gases. Okay, so every equation here, even though on the paper we just see it proceeding in one direction, remember everything can proceed in one direction and then proceed back in the other direction. So what would happen when the blood circulates back to the lungs is this bicarbonate ion would come back into a red blood cell, chloride would leave, it would join with the proton here, the hydrogen ion here, and it would form carbonic acid. Then it would break down with the help of an enzyme into water and carbon dioxide would then leave the body. So the majority of carbon dioxide is going to go this pathway, 70%. Continuing on with these dynamics of breathing, a couple of terms that you need to be somewhat familiar with, and I bet most of you have heard of the term apnea, but these are terms dealing with breathing. Now, most of us heard the term sleep apnea, which means we've quit breathing in our sleep, and of course this can lead to a lot of health risks. Hyperpnea means that we're breathing very heavily, and of course exercise, where we've depleted our oxygen supply, so we need more to come in, will usually cause us to have vigorous breathing. There are some other factors, even the sympathetic nervous system kicking in will often make us breathe harder to get us ready for the emergency. And eupnea is basically when you're normal. So here we've quit breathing, here we're breathing more than normal, and here's normal. Now, two other things that usually have a lot of medical implications to them is hypoventilation. Hypo means below, so extremely slow, shallow breathing, or hyperventilation, which hyper means more, or so hypo, below or less, hyper, more, and hyperventilation would be deep or rapid breathing, and usually that occurs due to an accumulation of carbon dioxide buildup or a lower pH. Now notice hyperventilation, which again, we kind of defined as this deep or rapid breathing due to the accumulation of carbon dioxide or low pH. Hyperventilation leads to increases in carbonic acid, and we call that, or excuse me,